Welcome back. In this video, we're going to go through our first related rates example together. And you can find this worksheet or this handout with these questions on Blackboard under the 2.8 related rates section called Worksheet Problems. There are about 5 that we'll go through. There's a spaced out version where there's some space for you to write your work if you want to print it or upload it to your tablet. There's also a condensed version that just has the questions. If you'd like to print these out and keep them in your notebook, do the work in your notebook. So the first page of this handout is a little summary of what related rates are and some general guidelines for solving related rates problems. So we kind of talked about all of these things in the first video. So the idea with related rates is that in all of the natural sciences and any kind of science, we have some quantities that are related, but vary over time. So here there are some examples, like the pressure of an ideal gas of fixed volume is proportional to the temperature, but over time, each of these quantities, the pressure and the temperature, change over time. And so the rate of change of the volume and the temperature will be related. So problems that involve the rates of change of these kinds of variables are referred to as related rates problems. Normally, we want to find the rate at which one of the variables is changing at a particular point in time, while we know the rates of the other variables and how they're changing. So the usual thing to do to start is to write an equation that relates the variables that are involved in the situation. And this will definitely, most of the time, come from some kind of geometric relationship that is present in the problem, or maybe some physical conditions that are imposed by the situation. Then we will differentiate this equation with respect to time little t, and we'll get a new equation called the related rates equation that relates the rates of change of each variable with respect to time. So the general guidelines are to first draw a picture, label everything, then kind of make a list of what you know and what you're looking for. So what is the known rate of change and what's the needed rate of change? Include units in this. The third thing is to come up with an equation that relates the variables that you've got from steps 1 and 2. Step number 4 is to differentiate this equation from the third step with respect to time. Then in step 5, the last thing you should do is substitute your known quantities into the equation and solve for the thing that you're looking for. So let's just stop talking about how to do these and actually do one. One last thing here I've got is some useful geometry formulas. So we've got the area and circumference of a circle, the area of a rectangle, area of a triangle, Pythagorean theorem, volume of a box, volume of a cylinder, volume of a sphere, and volume of a cone. So I'm not saying that you'll need to use every single one of these. These are some formulas that appear pretty often. So I guess just to make sure that we know what all of these shapes are, right? So this is a circle. Here we've got a rectangle. Here we've got a triangle. Right here we've got a right triangle. So this is the Pythagorean theorem that relates the lengths of the sides. Here we've got a 3D box. This one next to the box is a cylinder. This 3D shape is a sphere next to that. And then we've got a cone as our last shape. Okay, so our first example says a small plant store is selling potted indoor plants. We know that the weekly demand or price, little p, and cost functions for selling X plants are given by little p equals 25 minus 0.02x and c equals 5x plus 200. Plants are selling at a rate of 20 per week. At what rate is the profit changing per week when 400 plants have been sold? Okay, take a sec to pause this and reread the question so that you understand what's happening. There's a lot going on here. As far as the general guidelines or steps go, we don't really have a picture to draw. I mean, if you want to, you could draw a picture of a plant, but it's not important in this case. Um, there's just no geometric situation that's happening. So let's go through and extract everything that we've got here. So in the first sentence, a small plant store is selling potted indoor plants. That's fine. Like there's nothing that we can extract from that mathematically to help us. The weekly demand and cost C functions for selling X plants. Okay, so per week, we have this price function and this cost function. Okay. Then it says the plants are selling at a rate of 20 per week. Okay, so here we have a rate. Now the variables that we have here, and just to keep track of everything, make sure that we're all understanding our economics variables, right? X in this case will be number of plants. Sold in a week. Right, all of this has to do with like weekly. Okay, then we have little p, which is the price of one plant for the customer. Capital C is the total cost weekly for selling X plants that week. Okay, so if this says that we have the plants are selling at a rate of 20 per week, that we need to kind of notate that as some kind of symbol. We need to translate this into a math symbol. So this is the rate of plants per week. Okay, so the number of plants sold per week, it's the rate of that. So we have, that goes with X, right? So this will be dx dt equals 20 plants per week. Okay, so over here we'll keep track of the rates. Okay, so we know X represents plants, and then we know that the rate that it's selling at per week is 20 per week. So dxct is 20 plants per week. Then it asks us at what rate is the profit changing per week when 400 plants have been sold? Okay, so we want to eventually find the rate of change of the profit. So we don't have rates for the price and the cost. We're not talking about those at all. That's okay. We do want to find the rate of change of the profit. So we're going to need a variable over here for profit. So let's call that capital P. So this is profit for selling X plants. Profit, I guess, weekly. So what we're looking for is the rate of change of that variable. So we want capital P dt. And we want that at a particular instant in time. We want to know dp dt when 400 plants have been sold. So when X equals 400. Okay, so we will always want to find the rate of change of something at a particular point in time when a certain variable equals something else. So we're taking like a snapshot like of the week when there are 400 plants sold, what's the rate of change of the profit? So we need some kind of relationship that relates all of these variables together. And we do have one of those, right? So we know that profit is revenue minus cost. Revenue is price times X. And so we can get a formula for profit by taking the price equation, multiplying it by X, and then subtracting the cost equation. I always recommend simplifying profit equations when you're working with them. So like distribute the X into the price, distribute the minus sign, and then we can combine the like terms together. So we've got x's to the first, so that'll end up being 25x minus 5x, that'll be 20, positive 20x minus 200. Okay, so we have a formula or an equation that relates the quantities that we're talking about, right? We've got X involved here, we're talking about profit. So here's the equation that relates our variables. Now what we want to do is differentiate this with respect to time t so that we can get a formula that relates the rates of change of the profit and X. And that's good because that's what we're kind of working with over here, right? So if we differentiate with respect to time, we don't want to plug in anything before we do that. I know we have this value, X equals 400, but they're not selling 400 plants every single week. This isn't a constant value. The X value can change. So we want to plug this in afterwards. Another indicator for that is that we want a dx dt involved. And if we plug the 400 in here for X, we're just going to get a number over here, and differentiating that won't give us a formula for anything. It'll just be 0. So we are going to take our equation here and differentiate everything implicitly with respect to time little t. So if you recall back from our introduction video, right, want to differentiate the left-hand side with respect to t, and then also the right-hand side with respect to t. So d dt of both sides. Okay, so on the left-hand side, the derivative of p, a variable to the first, will be 1. But then we have to multiply this by the derivative or rate of change of capital P. And so that's dp dt. Okay, then on the right-hand side, we'll differentiate the negative 0.02 x squared to get negative 0.04 x to the first. But then we differentiated implicitly this x, so that needs a dx dt multiplied. Then we'll add the derivative of 20x, which is 20. But we differentiated apart with x, so that needs a dx dt as well. And then we subtract the derivative of 200, which is 0. Okay, so here's our related rates equation. We've got dp dt equals negative 0.04x dx dt plus 20 dx dt. Now we want to find the value of dp dt when we plug in 400 for x and we plug in 20 for dx dt. So it looks like at this point, all we want to do, now we can plug in the values that we have. Okay, so we have dp dt on the left-hand side. We're going to plug in 400 for x and a 20 for y, dx dt. And let's see what we get. Negative 0.04 times 400 times 20, and then we'll add 20 times 20. And that comes out to be 80. I want to make sure always that we include units in this. So I like to leave off the units till the very end because it gets a little clunky if you try to substitute them into the, like the equation and everything. So just think about what the units of profit would be and what are the units of the little t. So profit would of course be in dollars, and the little t is measured, the time in here is weeks. So it would be $80 per week that their profit is increasing when they sell 400 plants per week. So this is our first example. It's a little bit different than more of the geometric ones. In our last 4 examples here, we will look more like the geometric type, more typical related rate stuff that's not economics based. So tune into those, and I'll see you then.